Temperature sensors. There's 3 different categories of temperature sensors that are covered in the reference handbook: resistance temperature detectors, or RTDs, thermistors, and thermocouples. And we'll go through all 3 of those in this video. So let's start with resistance temperature detectors, or RTDs. These are probably the simplest of the 3 types in terms of the analysis, because the relationship between the resistance measured and the change in temperature is linear. Now, strictly speaking, that may not be true because there's a second constant. There's 2 constants of thermal resistance, alpha and beta, but beta is often ignored, and that is the guidance in the reference handbook as well. So we get a pretty good approximation by using alpha only, and we can basically take the equation that they give us in the reference handbook as gospel, and we can just say that R sub t, and we'll go through each of these variables, is equal to R sub 0 times the quantity 1 plus alpha times the quantity t minus t0, where R sub t is the resistance that's measured at some temperature. So we'll just call this the measured resistance. R0 is the resistance at T0, which is the reference temperature. So let's note that here, T0 is the reference temperature. And usually, unless otherwise specified, that reference temperature is going to be the freezing point of water, which is 0 degrees Celsius or 32 degrees Fahrenheit, depending on what set of units you're working in. And T is the actual temperature that we're trying to measure, and alpha is just a constant. We can call that the coefficient of thermal resistance. And again, we're only going to use alpha for the FE exam based on the reference handbook guidance. There's sometimes another constant offered called beta, but we're going to ignore beta unless specifically told not to in the problem statement. And the reason we're able to get this linear relationship is because of the construction of RTDs. They're typically made of a metal covered with a ceramic, and the reason they're covered with the ceramic is to give it a more stable reading. But it's a material property of that metal that's being selected that the relationship between the change in resistance and the change in temperature is linear, such that this formula will basically hold up. Of course, this isn't perfect, so there's going to be some tolerance. And in the reference handbook, you'll see a little chart that shows you the tolerance for different types of RTDs, and it's a function of 2 things. It's a function of the actual temperature that you're measuring, because the metal may not perform the same at different temperatures, and it's a function of the class of the RTD. They come in 2 classes, A and B. So take a look at that chart. They give you the tolerance on 2 different vertical axes. One is the change in the resistance, and the other is the change in the temperature in degrees, so you can look at it either way. The next type of temperature sensing device that we may have is the thermistor. And unlike an RTD, the thermistor has a nonlinear relationship between the resistance as a function of temperature. So it's not going to be a nice clean equation like this with 1 constant in it multiplied by the delta T. It's typically an exponential function, and the reference handbook gives us this equation: R sub t equals R sub 0 times E raised to the beta times the quantity 1 over T minus 1 over T0. And the variables are the same. R sub t is the measured resistance. R sub 0 is the resistance at the reference temperature. T sub 0 is the reference temperature. And T is the temperature that we're measuring. The only variable we haven't discussed is the constant beta. And beta is a function of the material that's being used in that thermistor, whether it's a semiconductor or a metal or an alloy. That value would have to be given to you by the manufacturer. So that's one way forward, is to use this exponential equation. But there's another avenue, and a second equation is given in the reference handbook. And I suspect that this is probably more common if you're actually dealing with manufacturers. I doubt they're going to give you an exponential relationship and 1 constant. I think this is more theory-based, so it might come into play. But in real life, we'll probably be using 1 over T, the temperature that we're measuring, is equal to A plus B times the natural log of the resistance measured plus C times the natural log of the resistance measured quantity cubed, where A, B, and C are constants given by the manufacturer. So they would have to be given in the problem statement for an FE problem. And based on some measured resistance, you could find out the temperature. You'd have to do this calculation and then take the reciprocal at the end to get T. And strangely enough, the reference handbook actually gives typical constants for A, B, and C. So those values are provided in the reference handbook. I find that a bit odd because I feel like thermistors probably come in all different kinds of flavors, but they make the statement that when the resistance is given in ohms and the temperature is in Kelvin, a typical thermistor might have these constants A, B, and C, and they give numbers. So you can check that out in the reference handbook as well. If you do choose to use those defaults because specific values are not provided in the problem statement, just make sure that you're clear that the temperature is in Kelvin. It would be a shame to do all this math correctly And then at the very end, pick the answer in Celsius as opposed to Kelvin. So if the answer choices are in Celsius, just add 273 to get the final answer. And the third and final type of temperature sensing device is the thermocouple. And the fundamental operating principle for the thermocouple is that it's comprised of two dissimilar metals that are run in parallel in an insulated cable. And there's a temperature difference across what's called the reference junction and the end of the thermocouple where you're interested in finding the temperature. So for example, let's draw our two cables in parallel. These would be put in the same insulator, but they're never in contact except at the very beginning. So these would be joined into a single node, and we call that the reference junction. And we know the temperature at the reference junction, T sub 0. And then on the other end of the cable, the temperature is being measured. Let's call that temperature T. And because the metals are dissimilar, even though the delta T is the same between the reference junction and the location where we're taking the measurement, there's going to be a difference in voltage across that length between the two metals because one metal will respond differently to the same delta T. Therefore, we can actually measure a difference in voltage across those terminals. And there's a name for this effect. It's called the Seebeck effect. You don't have to remember that. But the fundamental principle here is that that voltage that's induced across the two conductors in a thermocouple is linearly related to the change in temperature, or the delta T, between the reference junction and the location where we're taking the temperature measurement. So you could say the voltage is proportional to some constant times the delta T. And if you make the reference junction a known temperature, like we did with the RTDs, we said it's typically 0 degrees C or 32 degrees F. Let's just work in Celsius and say it's 0. Then the delta T is T, since we're just subtracting 0. And that's the way thermocouple data is offered up by manufacturers for simplicity. They always make the reference junction 32 degrees Fahrenheit, so the freezing point of water, but actually they offer the data straight through that point down to 0 degrees. So you'll see another chart in the reference handbook, which on the vertical axis has the output of the thermocouple in millivolts. It says EMF output, so it's millivolts on the vertical axis, and then temperature in degrees Fahrenheit on the horizontal axis. And depending on the material, or the pair of materials really, because there's two conductors in a thermocouple, there will be a linear relationship that starts from 0, but the slopes are all different. So these are all different thermocouples with different properties. And some of them are slightly nonlinear. I'm looking at one that has tungsten and a tungsten alloy, and it's got a bit of a curve to it. But for the most part, these are predominantly linear relationships. So the fundamental principle holds up, and the voltage measured is proportional to the difference in temperature that we're measuring. So that's a quick overview of RTDs, thermistors, and thermocouples.